Well, now let's take a look at the rational function f of x equals 1 over x squared. We've already seen what happens with f of x 1 over x, the reciprocal function. This one can almost be thought of as taking the reciprocal of x and squaring it. So, what is the domain of f? Well, you'll see that the domain is the same as f of x equals 1 over x. The only problem is when x squared is equal to 0. And that only occurs when x is equal to 0. So the domain is all real numbers except for 0. Now when we graph it, you'll see that 0 is the only point, the only x value where the function is not defined. So I'm just going to make a table of a couple of values. Let's do x and y, and let's do something like 1/4, 1, and 4. Okay, so actually let me change it to 1/2. 1 and 4. So 1/2, what is 1 over 1/2 squared? 1/2 squared is a fourth, and 1 over a fourth is equal to 4. So one ordered pair on the graph is going to be 1/2 comma 4. And then 1, when you plug in a 1, you get 1 over 1 squared. 1 over 1 is 1. And then finally, if I put in a 4, I'm going to get 1 over 4 squared, which is 1 over 16th. So with those three ordered pairs, I don't need to do too many because part of the graph is going to look similar to the graph of 1 over x, as you'll see. Well, let me graph 1, 1 first. And then if I go out to 4, x value of 4, the height is 1 over 16, basically almost 0, or I should say close to the x-axis. If I went out to 10, 1 over 10 squared is 1/100th. I would have to go up 1/100th of the way from here to here. It would be almost on that x-axis. And then when I plug in a fraction, say 1/2, with the function 1 over x, we went up 2, but I'm going to go up 4 in this case. And as you can see, it's going to look something like this. And again, that's not a very smooth graph I drew. It's never going to touch the x-axis, although it'll get close as you want to get. And it'll never quite touch the y-axis either, even as x gets really close to 0. Well, I could really stop at those points because, and I'm going to ask this question in a minute, maybe we'll get it over with right now. Let me just do it this way. What happens if I plug in -1/2, -1, and -4? I'm going to get exactly the same value of 4, 1, and 1 over 16. Notice that the x value is being squared, so if I plug in a -4 or a +4, I get out exactly the same value. This is an even function. Another way of writing f of x, it'd be x to the -2 power. Remember what this means? The negative says take 1 over x and then square it. 1 over x squared is this. So this is an even function. I didn't even need to make this table of values if I didn't want to. I know that even functions are a mirror image about the y-axis. So it'll go something like this. Oops. Again, not very smooth, and it shouldn't be touching the x-axis or the y-axis, but it should be pretty clear that this is a mirror image about the y-axis. All right, so that's the graph of the function f of x equals 1 over x squared. Let's ask a couple of these questions that we looked at earlier with the reciprocal function. By looking at the graph, what does f of x approach? The value of the function, the height of the function, what does it approach as x goes to infinity? The height of the function, it's approaching the x-axis, which is a height of 0. And let's go ahead down to the third one. When x goes to negative infinity, what's the height of the function approaching? 0 as well. It's approaching the x-axis. And now, f of x. What does it approach as x approaches 0? As x is approaching 0, from the right-hand side, from the plus direction, from the right-hand side, blowing up to positive infinity. And this time, I think this might be the difference between f of x equal 1 over x squared and f of x equals 1 over x, is this next one. When f of x goes, what does f of x go to as x goes to 0 from the negative side? It blows up to positive infinity as well. If you recall, the graph of f of x equals 1 over x, the left part of it was down here. And it approached negative infinity as x approached 0 from the left hand, or the negative side. And I've already answered this question. But is f of x equals 1 over x squared an even, odd, or neither? It's an even function because it can be written like x to the negative 2. Anytime all of the terms have even exponents for x, it's an even function if all of them do. All right, so that's again the graph of f of x equals 1 over x squared. Now let's learn a couple of new terms that we'll need for graphing purposes. Okay, the vertical line, remember all vertical lines are x equals some number. The vertical line x equal a is a blank of a function f. If f increases or decreases without bound as x approaches a. In other words, f of x, the value of the function f of x, or the height of the function, approaches either positive infinity or negative infinity as x goes to a. That means that this vertical line x equals a is a vertical asymptote. A vertical asymptote. And just to go back to this graph for a second, do you think there's a vertical asymptote in this graph? Is there a vertical line, or is there a value of x where as x approaches that particular value of x, the height of the function increases to infinity or decreases to negative infinity? Well, sure. This vertical line, which is the y-axis, the vertical line x equals 0, is a vertical asymptote. As x gets close to 0, this gets closer and closer to the y-axis without ever touching it. Okay, so if f of x is a rational function, the polynomial p of x divided by the polynomial q of x, and they've been reduced. They have no common factors. And a is a 0 of q of x. A is a 0 of q of x. That means that q of a equals 0. Then x equals a is a vertical asymptote. So they're easy to find, the vertical asymptotes. We'll go right back to this previous example for a second. Where is this function not defined? At 0, at x equals 0. And the vertical line x equals 0 is the vertical asymptote. That's how you find them. So let's look at these simple examples just to find the vertical asymptotes. We're not going to graph these four functions, just find the vertical asymptotes. Well, you only need to look at the denominators. And what value is not in the domain here? When is this denominator 0? Well, when x is equal to 0. So the vertical asymptote is the vertical line x equals 0. That's the y-axis for this one. All right, the vertical asymptote for g. Well, we're going to set this equal to 0 and see what we get. What do you get when you say x squared minus 1 equals 0? That means x squared equals 1, and by the square root property, that tells us that x is equal to plus or minus radical 1, or plus or minus 1. I'm going to write them separately because we've got that vertical line and we've got this vertical line. There are two vertical asymptotes for this function. All right, let's go on to the function h. Some of you probably already have the answer. When is x squared plus 1 equal to 0? Well, if you subtract 1, that means x squared is negative 1. That's never. There's no real number you can plug in to square it and get a negative 1. So I will say no vertical asymptote. And then for our last function, we look at the denominator, looking for a vertical asymptote. So we set the denominator equal to 0 and see if there's any way we can make that happen. Well, I hope this can be factored. X, and it has to be a minus minus because it multiplies to positive number and it adds together to a negative. And I think 5 and 1 would do it. So you set those equal to 0, and our vertical asymptotes are x equal 5 and x equal 1. Again, two vertical asymptotes. So we've seen examples where we have no vertical asymptote because the denominator can never be a 0. One vertical asymptote when it was simply x in the denominator. And then two of the examples had two vertical asymptotes because there were two values that could make a 0 in the denominator. And once again, it's the same. You're using the same brain cells to find the vertical asymptotes as you are to find the domain. What's the domain of this function? All real numbers except for 0. The domain here is all real numbers except for 1 and negative 1. The domain of this one, all real numbers. This denominator can't ever be a 0. The domain of this function j would be all real numbers except for the number 5 and the number 1.